Even if in the audience most of the people know what are reactive oxygen species and reactive nitrogen species, I wish to make a first series of slides to really speak about what I am speaking of and what I am not speaking of, okay? Because sometimes it's very confusing. So originally, the problem of oxidative stress came essentially because of the atomic bombing in Hiroshima and Nagasaki. And people realized that a lot of people have been killed by the bombing, but many other people have been killed afterward here. And that also with what has happened to people like the family Curie and so on, with a lot of cancer, people realize that when you have these high radiations, UV radiations, okay, so suntan is good, but not too much, okay, and radiation rays like are emitted during the radioactivity, you can have the splitting of the water molecule, and that generates a radical OH dot. So it's basically what it is done in pulse radiolysis. And now this OH dot radical is generated from the water, so it's generated statistically at every place in the cell, and there is not a special place where it is generated. It's just a probabilistic event. And when it is near, since the bound OH in the water molecule is the strongest bond that involves hydrogen in organic chemistry, and because of that, OH dot is able to abstract hydrogen atoms from any biomolecule. So we know, for example, I was speaking about cancer, any problem with the DNA, but also with the proteins that are reading the DNA or making functions, but also with the lipids that protect the cell, that are the cell membrane, so that creates problems. For example, that may be an issue for a lot of disease like Alzheimer, for example. You have plenty of damage, but this is related to this guy, which is generated here at one point in the cell and will hit immediately on anything which is not water here. So that means that this guy cannot survive for a long time. So he will kill, and if it does not find the means of generating a radical chain carrier that will transport the radical process, in fact that will die very quickly, unfortunately for us, okay? So, but for a long time people have been thinking exclusively in terms of OH dot radical, and evidently in chemistry people say, haha, I know a way to generate OH dot radical from hydrogen peroxide. This is a Fenton reaction. So from this OH dot radical, which is coming from the, I would say, radioactive view, we shifted to the Fenton reaction. But now a Fenton reaction, it needs that you have hydrogen peroxide, this is true, but it needs also that you have a catalyst. And this catalyst, as you know, are transition metal like iron and so on, okay? And those transition metal in the life, in the biology, they are sequestrated to avoid the Fenton reaction. So unless you have problems with the sequestration of these metals, the Fenton reaction is highly improbable, except in very some specific place where you have a lot of iron, like nucleus, for example. But hydrogen peroxide should not go easily to the nucleus of the cell. So that, when I started in this area, was really puzzling me, and I wondered what it is really, this oxidative stress. How comes that everybody is relating to OH dot, although the probability to have OH dot is extremely small, even if it is very, very reactive. And in fact, we have a power central to generate our energy, and this one is working on the oxidative stress. So for example, this is a mitochondria, and the mitochondria, if you look the membrane here, in between the inner compartment and the outer inner membrane and the outer membrane here, this guy is getting, he is working like my car, okay? He's getting carbohydrates, or I would say CH bond, okay? And will generate carbon dioxide, okay? And in this process we generate electrons that are carried to a sequence of proteins that are using these electrons to drive protons out from the inside to this inner compartment here. And in this inner compartment, this proton gradient will be building up, and that will be used then to transform ADP, which is missing here, into ATP, which is energy currency in the cells. So, but sometimes there is not enough ADP, for example, like here, and then it cannot work this way, and you have to release this gradient here, and you do it by using the electrons to make superoxide from oxygen that will be converted ultimately into water. So this is already one source of the oxidative stress. Also, if one of these enzymes is impaired for some reason, the mitochondria will call the nucleus. It is said that this is by sending messengers that are reactive oxygen species and reactive nitrogen species, but it's something which is very ambiguous because we don't know really what are those messengers. But anyway, if the mitochondria does not receive the corresponding protein from the nucleus, it will decide that the cell is impaired, and it will decide to kill the cell by generating caspase, and caspase will start the beginning of apoptosis. Apoptosis will amount to cleave the cell into little compartment. Here you see this was a macrophage. You will see macrophage after is cleaved. Its membranes start to be completely cleaved. Even the nucleus is cleaved and so on. And the cell will be completely disappearing, dismantled into the unit components that will be digested by macrophage. And this is basically what is happening in Alzheimer, okay, with the neurons of the people who are Alzheimer. And so it's a big issue to understand what makes this beginning of the apoptosis. And another place where this oxidative stress is very useful for our organism is to protect ourselves. So this is the basic level, I would say, the fireman of the organism. These are the macrophage, okay? And this is a nice macrophage, I would say, like our kids when they are 18. And that is when they register in the army and sent in Afghanistan, for example, okay? So they receive training here. Biologically, this is, for example, by interferon gamma and LPS that makes the macrophage believe that they are terrorists around. So he will go and try to catch this terrorist with this big extension of the cytoskeleton that makes extension of the membrane, and it will generate these vesicles. And for example, you can see here what this is taken from the internet, okay? One macrophage has smelled the Candida albicans, and he start to wrap around the Candida albicans up to the point where he has completely wrapped the poor bacteria inside, okay? And when he does that on its membrane, he has two essential devices, a pool of NADPH oxidase and a pool of enosynthase. When he wraps around here, he will create a vacuole, which is called phagolysosome, okay? And this is activated by calcium. At this moment, NADPH oxidase will generate superoxide, enosynthase will generate nitric oxide, and that will make an incredible cocktail that will kill the bacteria by cutting the bacteria into pieces up to the point it is digested. So that explains why we have maintained. First, we breathe oxygen. Okay, so again, if I take like the example of my car, when I am in my car, I have an engine and a tank of gas. Okay, if I cannot control, if my engine cannot control finally how the gas is given to the engine to power the car, everything could blow. Okay, you can go to your favorite gangster movie and you will see what is the energy coming out of your car when you are not controlling the system. So the system is controlled in our body by many things that you have only to open a magazine and you will see all this anti-radicals business, okay? So for once, advertising is not really telling the wrong things, okay? Fortunately, most of them we eat and they go away about the same way as they have entered, okay? So we do not make a real mess in our system, okay? So, by the way, all the business about the vitamin C that twice Nobel Prize was using at high concentration does not work, absolutely, because vitamin C is controlled in your blood to remain at not beyond the value, which is a normal value you get when you eat oranges and so on. So every pill of vitamin C that you take, like I'm doing in the morning, okay, is going away. The stuff was made for injection of vitamin C in the blood, which is completely different, okay? It has not been filtered by the guts and so on. So all these here, carotenoids, you have enzyme like a catalase molecule, glutathione and so on, vitamins, all these things are here to equilibrate the good thing, the good and the bad, like in the title of this thing. So when the good and the bad are equilibrated, this is called homeostasis, and we are perfect. Now, if we don't have enough of the oxidative stress, we are impaired, and for example, our macrophage will not be able to get rid of the bacteria. And for example, you know that what happens, for example, this is when the macrophages are impaired. This is, for example, what happens when you have AIDS. So on the other hand, if you make too much of them, they will create problems, and that result in a lot of illness. So it's very delicate, and it's very important that we understand what it is, this thing, and how it works. Because for a long time, the biologists and the medical people were just calling reactive oxygen species, reactive nitrogen species, okay? But what were these people? It was very hard to understand. So many years ago, we decided with my friend Monique Vuillaume to develop, to apply the methods that Mark Whiteman and myself introduced for the detection of neurotransmitter release that I call the artificial synapse. Why it is, I call it artificial synapse? Because in the synapse you have the neuron that is releasing a very small amount of molecule into the cleft. And here you have the receptors. So now, because this volume is very small, the actual concentration of neurotransmitter in the cleft is very high. And so the probability is that one neurotransmitter hits one receptor is extremely high. So with Mark, we adopted this method by bringing an electrode onto a living cell. So the electrode will collect everything which is electroactive. And here, for example, you have it in the case with the electrode is put over a macrophage that has been activated. And this is what we see. For example, this is one of these vesicles here emptying into the extracellular fluid. So in this thing, you have a lot of noise because you have 10,000 molecules, okay? So this is very critical, and here it is at the level where we catch the peroxynitrite, okay? So this is peroxynitrite or hydrogen peroxide. But because of these species that are born out of the superoxide and the nitric oxide, so superoxide will lead by disproportionation to hydrogen peroxide, or it can react coupled with extremely fast with nitric oxide to give you peroxynitrite, and this one can go out or decompose into nitrite and nitrates, okay? And it can also, nitric oxide can also diffuse. So in fact, formally, we get in all the release, we get these people. At longer time, this one will be able to undergo a lot of reaction with carbon dioxide, with thiols and all these things. But what is important is at the beginning, when we look at this thing, we have with this platinized carbon electrode, we have definite voltammograms for each of the 4 species. So by making measurement on a statistically significant series of cells at 4 potential, one here, which is close to the top of the hydrogen peroxide wave, but still the bottom of the peroxynitrite, one here, which is on the top of the two, on the plateaus of the two of this one, then here on the plateau of the nitric oxide and one here on the nitrate, we can reconstruct each of the components here, and then we can reconstruct how much of superoxide was here and how much of nitric oxide here. So for example, for the same macrophage that I showed before, statistically, so now is not a noisy curve and so on, you can see that these macrophages are producing nitric oxide and superoxide ion are approximately the same amount. Okay, so in most of the cells that we have been investigated, we have found that. So each time the two productions are almost equivalent. So some cells make more of both, some cells make less of both, but generally it's always like if the two systems are coupled. Now, one of the things is when this macrophage, as you have seen, he has these vesicles, it has been argued in the literature that maybe when he has these vesicles, some of the oxidative stress species, so some of these reactive species and can diffuse out and be inside of the macrophage. And this is an issue which is not completely idiot, because nitric oxide can diffuse through membranes. Okay, so you can expect that if the phagosome is limited by its own membrane, nitric oxide can diffuse out. Peroxynitrite is an anion. It should not diffuse out into a membrane, which is lipidic, but its pKa is 6.8. As a result, it can protonate very easily and diffuse out because one of the forms of the protonated forms is lipophilic and can diffuse out of the membrane. Hydrogen peroxide, it will be more difficult. Nitrite ions, they will not diffuse. Okay, so the question that was raised in the biological and medical literature was not a silly question, but the big problem was in order to investigate inside of the cell and not outside of the cell, when here we investigate when the vesicle is opening these vesicles are opening to the outer world. So we needed to make very, very small electrode, and for that we collaborated with Mike Mirkin in Columbia, in New York. And here you have, so we needed, basically if you look to this electrode, but now you think it's nano electrode, you make a little well here by attacking the platinum. This is platinum. And this well is perfectly defined here, and then you will grow black platinum inside of this thing, and here you see, for example, an AFM. This is a black platinum coming out of the well. And now this electrode, you can enter, for example, here on this classical horse of the electrochemistry, you have the beautiful curve here for the reduction of ruthenium. You enter into the cell, since the electrode is small, the cell seals. No ruthenium can fill in the cell, so you have no current. And now you pop up the electrode out of the cell and you get the green curve here. So it means that you can enter the cell, okay, with these electrodes that are different from those of Mirkin in the past, because they have this black platinum, and the black platinum is not really affected by this transfer, and presumably this is when it's going out that we are losing a part of the reaction. So now, for example, what is important is to compare what we can measure inside of the cell compared to outside. So this is one of the signals, for example, outside of the cell here. At this potential you get all the species: hydrogen peroxide, peroxynitrite, nitric oxide, and nitrite ions. Okay, so outside, this is what I shown before. You see, you have a very huge curve with a large quantity, but inside now we get very small curves. Okay, so you can is about 1/20th to nearly 1/100th of the one that is shown outside, and you have a rising here. Okay, those are two typical curves, but you have a rising period, and immediately after this rising, you have a kind of exponential tail, and this exponential tail is the same as this one, which shows that the macrophage is able to detect immediately that something has been leaking out and is cleaning that. So that shows why people were having this hypothesis, but nobody could report that inside of the macrophage you had a huge oxidative stress, because presumably the macrophage does like a poor plumber, okay? You make a poor plumbing, you have leaks, but you clean these leaks, okay, very quickly. From that, I will shift to a case in which oxidative stress is important, and this is the application to bond maintenance. I don't know what you know about bonds, but if you know as much I was knowing before becoming interested to this, that was just a bond, is a piece of stone that we have in our bodies that holds us, okay? And is a kind of flexible stone because of the protein inside. So that was basically what I was knowing about the bonds, okay? So basically that, okay? And here you have the mineral part of the bond here, and this is the tissue. So where the mineral part is mixed with organic part, and bioorganic part that gives the possibility that the bond, for example, if my bonds were really in the calcium phosphate of the matrix, if I just do like this, my bond will simply split apart and I will fall on the ground. That will please many people, but this is not the purpose of this talk, okay? So I was taught that all this organic material which is here is a kind of glue and make a kind of spring to absorb the notion. But in fact it's more complicated than that. Because this notion that the bond will break is exactly true. Our bonds are never the same. So each time I am moving here, or you are sitting, you are breaking your bones in your ankles and so on, you are making little cracks. These little cracks will activate cells that will immediately reconstruct the bone locally, okay? And this is the way we can have the feeling that we have a skeleton which is same skeleton, but in fact we are rebuilding this skeleton. It's like this convention center. If you had people destroying the walls and in continuous reconstructing it, so in 300 years from now, it will be brand new. If you let this thing this way, if you come in 50 years, you will see a bunch of concrete and ruins, okay? So, basically we have three kind of cells that operate in that. The osteoblast, that secrete the osteoids, so which is the material for the bone matrix, and they begin the mineralization. So these are the cells that are constructing the bone. Now you have the osteoclast, that are the people who are degrading the bone. Because in fact when you construct the bone, think of this wall. If you have people who are building this wall in continuous, there will be always some smart people that think that maybe the wall should be thicker, okay, and start to make a thicker wall. But then this will create a problem for other things. So these cells feel the pressure of the matrix, bone matrix, and when they feel this pressure, they decide to degrade the bone. Okay, and in fact when women have osteoporosis, is a big problem because that is still active, but this one start to be not active because it's under control of hormones, and this is why older women with osteoporosis, they have the bones that start to be with in French is dentelle, okay? Brittle, and but they look like with a lot of holes, like you know, this kind of tissues that women use for bras, okay? Which are full of holes, yeah?
Osteoporosis.
What?
Osteoporosis.
No, but
he's trying to explain how the bone looks with all the holes in it. Porous?
Yeah. Okay, anyway, this was not what I wanted to say, but it looks that the classical American male does not know how he's made in palm.
Oh, you're talking about lace? No.
Lace.
Yeah,
lace.
okay.
So if you compare a real tissue cloth to lace, this is about my bones as compared to a woman of 70 who has osteoporosis, okay? So you can understand that will break very easily. And so then you need to have this balance here between the bone resorption, okay, because otherwise the bones will grow and that will be a cancer, okay, and the bone formation here that and the whole thing should be equilibrated. And to my surprise, the biologists and the medical people were saying, this is the bone formation is under the control by nitric oxide, but the bone resorption is under control by hydrogen peroxide. And you remember what I told you in our former studies, we were always finding an equivalent proportion of superoxide and nitric oxide in any cells. So at the beginning when I read that, I said must be something different because it cannot be possible. All cells that we are investigating are making always these equal proportions. But already, if you go, we studied these MG63 cells that are cancer cells, bone cancer cells. They don't have the NADPH oxidase. They have, so already they will decrease production of superoxide. This is replaced by xanthase, which is also producing superoxide, but to a lesser level. And they have enosynthase. So you can always think a lot, but the best is to do the experiments, okay? And we decided to use the classical method. So this was done with my friends in the lab in Xiamen, in China. So this is a MG63 cell in this cartoon. We stimulate the cell, okay, and we measure what the cell is releasing. So here you have one of the cell here, which is like this. That is the electrode, which is out of focus. Here the electrode is pushed above, and you have the pipette, which is used to stimulate the cell by creating the depolarization of the membranes to let enter calcium. And this is after the experiment, so you see that the cell has not suffered at all. Okay. And now, when we make the measurement, like I said before, we measured all the people who are coming out. Okay, and when we reconstruct the flux, you see already we find a very small quantity of hydrogen peroxide, 2 femtomoles. This is per one cell, okay, in average. And 6 femtomole of peroxynitrite, 17 femtomoles for nitric oxide, and 5 femtomoles for nitrate. So immediately you realize that this is nitric oxide, okay, is coming from the nitric oxide, and this one is coming from peroxynitrite. So that makes a huge amount of species that are coming from the production of nitric oxide. And in fact, if you count back here, you will find that this cell in average is sending about 30 femtomoles of nitric oxide and only 13 femtomoles of superoxide. So it is completely unbalanced as compared. So now what we want to do is to investigate other cells to see if they generate more hydrogen peroxide. If it is this way, maybe we can think of some medicine that could be, because there are a lot of organic molecules that can be used to deliver nitric oxide. So maybe we can think of some implants that put in the bones of people with osteoporosis, so they will generate this nitric oxide and maybe stimulate the bone formation that cannot go because of the hormonal track has been impaired after the menopause. So on that I wanted to conclude. I wanted to leave, since I tried to make this talk rather provocative, I have left some time for the discussion, and I will thank the people who did this work. So essentially in École Normale Supérieure, in my laboratory, this is Dr. Manon Guille, who is now assistant professor, and Frédéric Lemaitre, who is also assistant professor. Larry Cole is one of the most brilliant postdoc I had in this area of bioelectrochemistry, and is now back in his country in Singapore. And Miss Song Lu, she is a doctor doing her PhD. She will defend her PhD in September. Like I said, this is a collaboration with Mike Mirkin from Queens College in New York, okay? And in her lab, this person, Xixian Wang, we call her Connie, she's on the doctor track. She is very good, and she did all these microelectrodes here. And she learned that platinum is not platinum. So that means that classical platinum wire and black platinum are two different things, and black platinum is essential for detecting all these things, okay? Jean-Marc Noël is now a postdoc in Mike Mirkin, and is working also in this project. And in the University of Xiamen in China, this is a joint lab between my friend John Chun Tian and my laboratory. So this is a symbol of this joint lab. And it was involving Professor Jian Lin, who is now retiring, and Dr. Ren Wu, who spent a lot of time in Paris. I want to thank Academy of Science, École Normale Supérieure, CNRS, the Ministry of Research, and the University Pierre and Marie Curie, since my lab belongs to the University Pierre Marie Curie, ENS, and CNRS. Finally, I want to thank Susan for inviting me to come here, and all of you for your kind attention. Thank you.
We have time for a couple questions. Yes, Dave.
So, how's the macrophage controlling? You said the macrophage shows intercellularly that it seems to be reducing the oxidative stress pretty quickly. Does it do it by having an overload of glutathione? How does it do it?
We don't know yet, because what this part, these few slides that they are on a work that has been finished only 10 days ago, and is submitted now to PNAS with Mike Mirkin. So I think, to my knowledge, this is the first time somebody is able to quantify something inside of the macrophage, and we hope that now we will be able to investigate that, to try to understand. And in particular, I didn't say when I gave my talk, but here we didn't use the already activated macrophage. You remember okay, this is the normal macrophage, not activated, okay? This one is activated. So my guess was that the macrophage, they can eat many bacteria, okay, in a row. So if they were killing themselves each time they eat bacteria, that would not be very efficient. So I am thinking that here already they have inside developed all the means to kill the ROS and RMS, okay? So that's the reason we use the rest macrophage in the rest state, and we just stimulate them by depolarizing the membrane by the entrance of calcium, thinking that the macrophage, I apologize for saying this way, doesn't know that it will be making oxidative stress. So what it is fastness to respond. And you can see from here that he responds in less than 2 seconds and cleans everything, okay? So now we will try to impair this cleaning by interfering with the macrophage. But this is a big research now. But thank you for your question. It's very important.
Any other questions? We have time for maybe one more. All right. Well, thanks a lot. Thank you very much.